So let's continue. So in this lecture, we're going to solve this related optimization problem in PCA. So this is mathematically, we actually want to solve this orthonormal basis of this subspace of V of this maximum and maximum variance problems. So the maximum problem and variance problem that we have is J from 1 to the D of Wj of transpose, X transpose of X of Wj. We're doing this maximization of W1 to WD, and so each W1 to WD is actually a vector in R big D. So this right here, we have a talk about this. So this is basically maximum variances problem. So basically, this is the covariance matrix of X, and we want to set and the point of everything is we want to find set of direction which is like W1, W2 to WD. They are orthonormal basis. If we actually project everything in these directions, I want to maximize the variances along these directions. But the key here is it's constrained that we actually subject to this W1 to WD has to be orthonormal. So that means my Wi transpose of Wj is actually 0 if I is not equal to j, if it is 1 otherwise. Right. So these optimal solutions, W1 star to WD star, they are called principal components. So that's why this is called principal component analysis. Principal component. It's called PC. And obviously, this is a very hard problem. We have, so this is so this is a quadratic. It's quadratic and objective. With this constraint here is and basically it's orthonormal constraint. And in particular for this orthonormal constraint, this is non-convex constraint. So as a result, this whole problem is non-convex. So I mean, this is basically a non-convex optimization problem. So this whole thing is very difficult. I mean, I'm actually a very difficult problem. So and let's start with a simple one. Let's start with d equal to 1. That means I only want to find just one first principal component. All right. So what does that mean? Is we only want to find W1 star, which is argumax of constraint. Since we only have a one principal component, so and we don't need to assume the orthogonality here. we only need to assume the W1 has the unique length. That it will be W1 transpose X transpose of X, then W1. Okay. So okay, so how to solve this? So the first thing is the solution. So let me show you, and tell you the solution that I'm going to prove it. So the solution of this problem is this W1 star is called plus minus or V1. It is the leading eigen vectors of the covariance matrices X transpose of X. So basically what I'm saying is satisfy this X transpose of X times of V1 equal to lambda 1 V1. Okay, so so what does that imply? Is all W1 transpose X transpose of X W1 is less equal than V1 transpose X transpose of X of V1 for all possible W1 with the unit length, right? So this is a very interesting and observation. So we want to, actually and prove it. So this whole argument here is actually has a name. It's called like Rayleigh's inequalities. So this is and this result is actually called like Rayleigh's inequalities. So how to prove it? So let's prove it. So the proof comes from the first thing, and the first observation is X transpose X is a PSD matrix, positive semi-definite matrices. So as a result, this has the following eigenvalue decompositions, which is Q lambda, Q transpose. So in particular, Q here is the orthogonal matrix. And the lambda here is a diagonal that lambda 1 to lambda d, they are bigger or equal than 0. Then if we have any W1 with the unit length, that means my norm of W1 equal to 1. This W1 transpose times X transpose X and then W1. This whole thing, we can plug in this eigenvalue decomposition. So this is W1 transpose Q lambda Q transpose of W1. And what I'm going to do is I'm going to define the Y equal to W1 transpose of Q. So that means this becomes Y. Sorry, I'm wrong here. I'm going to define this as being Q transpose of W1, then this becomes Y transpose lambda of Y. And also the norm and the square norm of Y is still equal to Q transpose W1 transpose, then Q transpose of W1. This becomes W1 transpose Q transpose W1. But we know Q is an orthogonal matrix. This becomes W1 transpose W1. This is square of the two norm of this. So we know this is equal to 1. So that means the Y is also a unit vector. So this whole thing becomes the following. So this whole optimization and becomes equivalent as we want to find argmax of Y transpose lambda Y, with Y is unit vector here. But the beauty of everything is this lambda here is a diagonal matrix. So so this is much easier to be handled because if we can write our Y is each component of Y1 to YD, then this Y transpose lambda Y, it actually becomes summation I from 1 to the D lambda I of yi squared, and it's subject to and the square of each component, to be 1. And we know all these lambda are ordered in the decreasing orders. So that means my lambda 1 is bigger equal than lambda 2, and so on. It is bigger equal than lambda d is bigger equal than 0. So what we can do is and trying to basically allocate my weight of my y1 to yd such that to maximize this whole component. It's quite clear the maximum is reached if we allocate my y1 equal to 1 and yi is equal to 0 for all the I bigger than 1. So then this whole thing, the objective function, will reach the maximum value. So then the maximum of y transpose y, this is nothing but just lambda 1. And the y, and the y star is just being one bunch of zeros. So as the result, if we want to recover the optimal W1 star, and what we can do is we know y is equal to Q transpose of W1. So if we multiply Q on both hand side, then Q times Y, that becomes W1. So that means W1 star will be equal to Q times Y star. So this is a Q, and multiply the Y has to be a column, so it's bunch of 1, 0. So this is nothing but this is nothing but the first column of the Q, which is B1 right here, right? Because this actually corresponding to the first eigenvectors of X transpose of X. Okay, so that's why and of course we can have the plus minus and a plus sign and a minus sign because sign of W1 doesn't matter. So W1 star as the solution of plus or minus W of V1. So that's how we prove this part. So this is the cases for the simplest possible one, which is the D so equal to 1. So when the D equal to 1, that we don't need to consider the like orthogonal constraints. So I mean everything will be significantly easier. But let's just relate everything back to back to the singular values. And we will come back to this a little bit later. So this is, I mean, a little bit review on the SVD singular value decompositions. Sometimes, so this, like say this MX matrix, which is my data matrix, is in form of M by D. And I mean, it's possible that we have seen in the past that we have so many features that this big D is even bigger and significant bigger than the number of points of N. Then in this cases, we are getting X transpose of X right here. That actually becomes a big D by big D. That will be too expensive to calculate or too large to store because that's order of D squared. So what we can do is instead of we find out the eigenvalues of and here like V1 is the and eigenvalues of X transpose of X. X. But this is also, we can use, I mean, a different approach is using the singular value decompositions of the data matrix. So we can use the SVD of X. We know singular value decomposition always exists for any matrix, whether it's a square, whether it's a singular, whether it's a fat matrix, whether it's a non-square matrix. So this will be U sigma V transpose. So in this case, it's U will be M by R. Sigma will be R by R. V will be R by V will be V transpose. Yeah, V will be R by like D by R. Right, so R is the rank of the matrices. And this is also a diagonal matrix. So R is the rank of the X. So in this and cases on the diagonal, they are all the singular values. So basically the sigma 1 is bigger equal than sigma 2 and bigger equal than sigma R. And sigma R, that will be strictly bigger than 0 because R is the rank of the and matrix of X. So the first thing is, if we actually trying to calculate the X transpose of X and use the decomposition of singular value decomposition. So X transpose of X, this is V sigma U transpose. U sigma V transpose. So this is V sigma square V transpose. And then, so that means the eigenvalue of X transpose of X is just equal to sigma 1 square sigma 2 square to sigma R square, right? So that means the first eigenvalue of X transpose X is nothing but sigma 1 square, which is the largest eigenvalue, or the lead and the lead as eigenvalues of X transpose X. So that means my V1. So and then the V1 is just the first column of the matrix V. V matrix. So that means my X transpose of X of V1 equal to sigma 1 square of V1, right? So we can take advantage of everything, and we can project all my datas onto V's, right? So project X X of I onto the V, which in this case will just be span of V1, right? So this is my X tubed of I. So this is inner product of V1 and X of I. So this is basically just V1 transpose of X of I. That's a scalar times of V1. So this is still in R big D. The actual low dimensional data representation low dimensional is we actually have to rotate, this axis V1 to be aligned with and rotate this like eigenvectors into our axes. So that will be my Z of I. Just simply take the weight, right? So this will be V1 transpose and X of I. In this case, it will be just a scalar. So, in this way, we actually project from very high dimension with a D onto just one dimensional and the representations. And of course, there will be general cases. The general cases, it's more complicated than that. So basically, and right here, we just focus on 1D. In terms of general cases, that will be W1 star to WD star. So general D. So we want to solve for W1 star to WD star. This will be argue max of W1 to WD of R big D, summation of J from 1 to the D of WJ transpose, X transpose of X, WJ. Right, subjected to WI transpose WJ equal to 0 or 1. If it is x is not equal to j, that will be 0. Otherwise, that will be 1. So this is the general optimization. We have a talk about this. In when d equal to 1, we prove w1 star is nothing but the v1 right here. For the general one, I'm not going to prove it, but let me just state the solutions here. The solution for this principal component of the solution, I'm using different color here. The solution is this principal component Wj is nothing but V of j, with j from 1 to the d. It's basically the first d columns of V. V matrix. I want to remind you this V matrix, it's nothing but the singular value decompositions of X. I mean, this V is called, it's called, what is that called? Yeah, singular vectors. It's like right singular vectors. So this is, and basically the singular vectors. Okay, so that means we can actually stack these columns of Vj, and then that becomes a matrix. So here we're going to like define the V and V, and define this Vd. So this V is a matrix V. What is like the matrix V is I'm going to stack the V1, stack V2 to stack VDs for each column here. Then that becomes a big D by small d matrix. All right. If we take this first d columns and stack them together, becomes a matrix. So we can solve for the data projections. So basically, we can project x of I onto V. Oh, I mean this V is the span of V1 to V1 to VD to VD, yes. Then my x shoot of I, it's nothing but we need to it's a linear combination of my Vj, but the weight is the inner product of Vj and x of I. So this is Vj transpose x of I, then Vj. Okay. And what we can do is we can stack them together, then and vectorize it. If we actually use the vectorized version, so this is using the V matrix D that defined above. Just take the first D columns of V, and transpose the X of Y. Right, so this is so this actually is still in R big D right here. So the actual low dimensional data representation is we can use Z of I, right? So what we can do is we can put everything, just taking the weight right here, just this weight will be crucial here. So if we actually take the weight and put into the vector, this is V1 transpose of X of I to VD transpose of X of I. Of course, this will be in RD. You can write everything in terms of matrix form. This is the VD that stacked matrix transpose times of X of I. Okay, so this is actually the low dimensional data representations. So, I mean, this is truly intrinsically low dimensional right now. All right, so here we are not going to prove it, just you can see we turns out can solve this and this like nonlinear and a quadratic and objective function with respect to non-convex constraint problem analytically. That's quite rare. There's a very few and the situations that we can solve it and it's analytically, which in this case is just being and the solution was just being the singular vectors of the X matrix and basically the first D and singular vectors of the matrix. So in terms of matrix and representation, will just be first D columns of and V's. All right, so we could use this whole idea to actually to see how good or how bad of our approximations. We can argue something called approximation error. Right, so I want to remind you, our X here is U sigma B transpose. It's basically summation J from 1 to the R sigma J Uj Bj transpose. And the sigma 1 is bigger equal than sigma 2, bigger equal than sigma R, bigger equal than 0. So if we take the first D, so this is n by D, big D. So if we take the and a projective matrix, okay, so the projective matrix, so this is just a vector right here, right? So this is just a simple vector. And we assume this is a column here. So this is not precisely what we think about, but nevertheless, if we're using the data matrix here, I mean, this X right here is, and each of X of I is a row, right? And at the end, there will be X of N. That means, I mean, so we need to take transpose directly. So this, then the projected data matrix onto V, which is X2 will be X times of VD and the VD transpose. Okay. So again, this is still a n by d matrix because we know X2 is still living our big D matrix. If we actually plug in this U sigma V transpose and the VD and the VD transpose, this right here, the first D columns take transpose with VD, that give me identity of the I, and everything else just give me 0. So this actually becomes the following. So U of D, so we just take the first and the first D column of U, because everything else and beyond the D, and it doesn't matter, just being like thrown away. And this sigma is also, we only keep the first D component, then becomes diagonal of sigma 1 to sigma D. Then this is VD transpose. And we can write everything in terms of summation. This is I from 1 to the D, sigma I, UI, and the VI transpose. So what is doing right here, if we want to like and extract things and compress the data, is just basically we extract the D most significant component of X and like throw away the everything else. What we are trying to do is, and you have seen that in the first week of the lecture. So this is nothing but the rank D approximation of X. So if we use this argument right here, this way to approximate, then the rank of X2 is in small d right here. Right, so this is basically we actually project our data into the subspace of V, which to ensure, and all my data here is actually, it's intrinsically and the small d dimensions. But in terms of matrices and formulation, and this is nothing but best and rank D matrix upon best rank D approximations to X, as we already talk about that in the first week of the classes. So the key here is, if my original data here are approximately like D-dimensional already. For example, if we actually plot the singular values, which in this case is just 1, 2, to here is big D, and then these are the singular values. And it is like little d here. These values are something like this. So we know all the singular values will be strictly bigger equal than 0. But at small d, the singular value is already very, very small, and everything else just so small that is close to 0, that we can say our like matrix of X is close to a rank D matrix. So we can tell from singular value plot that in this cases we call X here is close to a rank small D matrix. i.e., so all these sigma j is approximately equal to 0 for all the j is bigger equal than d plus 1, smaller or equal than r. R is the rank of the matrix. So that means beyond the d, and from d plus 1 to the rank of the matrix, all of my singular values are close to 0. With that, we argue this is very close to, and this whole data matrix is close to a rank D matrix. That, if we have that, then the information that we lost so we can quantify this information that we lost by taking this x minus x2 in terms of Frobenius norm. This is equal to x minus xvd and xvd transpose in terms of Frobenius norm. We know the top one, this x will be summation of j from 1 to the r sigma j u, and we can write everything in terms of like literary summations formula of the singular value decompositions. However, for x2, here we truncate up to the rank of d, then this will be j from 1 to the d, sigma j, uj, bj transpose. So this becomes j from d plus 1. This is r here. I missed r. Of sigma of j, uj, bj transpose of the Frobenius norm. This Frobenius norm is nothing but we think about this is sigma d plus 1 to sigma r as whole vector. We take the 2 norm for that. Right, so this becomes square root of summation j from d plus 1 to r or sigma j squared. Right, so we know each of this, if everything is close to rank D, these are all very close to 0. Then square sum, then take the square root, which is the and rooming square of all the remainder singular values will also be very close to 0. So if x is close to rank D matrix, then the information that we lose will be very small. So this also gives you guidance how we should choose the D's, right? So we should plot the singular values of x and truncate my D to some point that beyond of D, all the singular values are very close to 0. All right, so that is PCA. That is the main point of PCA. Let me just actually demonstrate that with the code. So right here, so we have this MNIST data set that is pretty large. So the first thing I need to do is need to subtract the mean. Right. So as I said, in general, this data of x is not, it's not very, I mean, it's not like centered at 0. The way we do is we need to subtract mean. if you actually want to reconstruct the accent or image, you need to add the main back, right? So you always need to remember, if you want to reconstruct that, you need to put the main back. Okay, the first thing that we do is we use eigenvalue and eigen decomposition of the covariance matrix. So basically, we calculate the covariance matrix. And we are taking this EIGH, which is eigen, and to find eigenvalues of Hermitian matrix or symmetric matrix. So we got all these eigenvalues and eigenvectors. We want to make sure all these eigenvectors should be real, because sometimes it gets you some complex numbers, but we know it has to be real. So we get rid of all the complex component. So this will be your B transpose here. And what we do is we need to sort all the eigenvalues in a decreasing order to ensure this is actually in a decreasing order. Then we have to reorder the columns of BH. All right, so this has to be ordered with the corresponding eigenvalues with the decreasing orders. So here we're just trying to plot this and eigenvalues right here. So we know this will be sigma squared. So you can see this right here. It's very interesting. So we know this is 784 dimensions. But this start to have a couple dominant and eigenvalues right here. Then eigenvalue drop to 0 very, very quickly. About maybe 100 or 200. I mean, that's already very close to 0. Okay, so that means for the most part of dimension of 784, we probably don't need 784 dimensions. What we actually need is only maybe 100 or 200 dimensions. Okay, so let's just choose like maybe first top 200 principal components. That means we basically says, I'm going to take the first and so like VH right here. So so right here, this eigenvector here is my my V. Yes, I mean it's my V right here. My VH here is my V transpose, right? Because we actually need to need to work on the V transpose. But if we want to take the first like component, which is the first 200 columns, that means we need to work with the V's. So that means we need to take transpose again. So VH dot transpose becomes the V. So we take the first 200 components, then we do this projection. So X dot components transpose. So this is nothing but what we are talking about right here, right? So this is the projector matrix. This projector matrix is still in high dimensions, and you need to be careful. You need to add this back and this X string back. So you can see this data is still like 60,000 by 784. You reshape this data to 60,000 to 28 by 28. You can actually plot this images right here. So this is first 4 images that you will get. You can see this is the image before you do the piece and the projection on the first 200 component. This is an image after we project onto the first 200 component. So everything on the right, it's about I'm intrinsically low dimensional with the D and a small d equal to equal to 200. On the other hand, everything on the left is still in and it's intrinsically in 784 dimensions. But of course, And this is just my X2. That means I'm still using like high dimensional data to represent these images. So if we actually look the time for PCA takes about 3.5 seconds. Time for projection, that takes about 2.3 seconds, which is quite fast. You can see the matrix rank. Quite expensive to calculate. Is 201. So the reason this 201 is because I add the mean back. So that's why for the rank of the first part, that will be 200. And once we add the mean back, so the rank becomes 201. So a second method that we can do is it's using the PCA. So in these cases, it will be slightly more expensive. It's just because my big D is not really very large. So that's why in a singular value decompositions, it's not shows the power. But if your big D is really large, like 60,000 or even more, then the first method will be extremely expensive because big D by big D will be too expensive to store. Right now, big D by big D is only 784 by 784. That is much manageable in the situations. But what you can do is you can just call the SVD of X. But here you need to make sure this 4 matrix is false, because you don't want to output this matrix of U and the VH into like gigantic versions. So and you want to do some like truncated and the economical version of the singular value decompositions. If you actually plot the singular values, you have the similar behavior. So this is actually the sigma. As a comparison, this is actually the sigma square. So that's why this plot looks quite different, but still like demonstrate this very good like structure that maybe first 200 singular values dominate the whole situations. Everything else is being like close to zero compared to those first couple and first 200 and singular values. So you can do exactly the same thing, right? So you can see this, the effect of the projections. It has the same quality. So the left one is the original one. The right one is approximate one with the top 200 principal components. Okay, so, and of course you will be curious, what is those like eigendigits? So that means we can take this top 9 principal component, then you can reshape to 28 by 28. You want to see what is those like components, principal components really look like. So this actually looks like this. So this has a name called eigendigits. So now, in fact, all these image to the like right column is intrinsically 200 dimensions instead of 784 without losing much information. You can actually apply all sorts of machine learning algorithms on this 200 dimension arrays. So this will significantly speed up your learning. This is particularly important if your big D is really, really large. Right now, big D is only 784, but like if you have really large D, this will be very helpful. Mathematically, there's no differences for you to calculate PCA on the data matrix or eigenvalues on covariance matrix. But differences is purely numerical positions or complexities. In general, applying the SVD is numerically more stable than the covariance matrix. So this is something that you need to keep in mind, particularly when D is really, really large, because when D is really, really large, D by D matrix is almost impossible to calculate. or to calculate and to store as well. Okay, so this is the hinge loss you have done. And previously we tried with the two different, like lambda 10 to the minus 3 and 10 to the minus 2. We have the same like learning rate we do, and we just do this 0 or non-zero, I think. Yeah. Sorry, I think we are doing what we are doing here. We are doing 9 or not 1 9, I think. Yeah, 9 or not 9. X and Y, X and Y, X and Y. Okay, so if we work with X and Y, that's sorry, that's a 0 on sorry, that's a 0 or non-zero here. That's a 0 or non-zero here. So and what we're trying to do on like hinge loss, so SBM with the hinge loss is we want to do like 0 versus non-zero here. This is the one that we work with a dimension of 784. That means we just and apply the original data of X. Has a dimension of 784. That take about 67 seconds. Right, we got this test error right here. On the other hand, we can perform the PCA to reduce dimensions. So this is what we are doing here. So we calculate the mean of X, then we subtract the mean, then we calculate SVD. Then we know this V right here is the VH transpose. And what we do is we calculate the Z instead. So this Z is actually intrinsically embedded in in 200 dimensions. So this is 60,000 by 200. So with this Z is not viewable. So this is actually lives in like 200 dimensions. So if you want to view this image, you have to put this base back, like what we are, and that we were doing for the X2. Then you can view like and each images. But for each Z here is just and each column will be kind of like data representation, low dimension data representations for each of data. So that means each row, like say Z1, is corresponding to a date and corresponding to a low dimensional representations of the X1, right? Okay, so this is actually the low dimensional representation. Of X. And of course, you have to do the same thing for the X test. You should never using the X test mean here. You should always use the same mean, so like you won't have the biases at all. So you always subtract the same mean for the training and the testings. Then you do the same thing for the testing, right? So this will be Z test will be dot product with X test and the V's. So this is the low dimensional representation of testing data set. Okay, so now the Z and Z test only have a 200 features instead of 784 features. So we do exactly the same thing for the hinge loss, but only with 200 features. And you can see right here, the time that we actually needed is only 53 seconds, right? Compared with almost 70 seconds. So that's about 14 seconds faster. And also in terms of test error, here is also smaller as well. Compared to with the full 784 dimensions. So the reason, as I mentioned, is if we're using PCA to reduce dimensions, not only we compress the data into lower dimension, it also removes some level of the noises in other dimensions. These dimensions has very small fluctuation noises. These fluctuation noises actually doesn't contribute to our classification or doesn't matter to our classifications. It might even further corrupt our predictions. This PCA not only compress our dimension into lower dimension, but also effectively filter out those noises out. So as a result, we will have a better test errors. In this cases, we are getting about 0.09 and versus 0.1. Okay, so you can see, this is a significant better as a comparisons in terms of speed and performances with PCA or without PCAs. All right, so this is just a simple illustrations. This whole thing is not necessary to be true, even and it's not necessarily work for all the datas. For some datas, you might see after PCAs, this performance is getting even better, and the whole performance is even faster. But there are also some situations that you will see that the performance is getting worse because when you compress the dimension into lower dimensions, somehow you throw out some informations that could be important for the classifications. So as the result, it might just be be really bad for our classifications. So you actually don't know for sure. So that's why you actually have to test it and to see whether your performance is better or worse. But one thing is for sure, if we compress everything from high dimension to low dimensional and to make any kind of machine learning predictions and classifications, the speed is definitely faster. So this is one thing is for sure. All right, so that's everything for principal component analysis. In the later, almost the last week of the lecture, we're going back to this PCA problems. I want to combine the PCA with something called LDA. So this is more like supervised version of dimension reductions. So this is kind of like as another new concepts I will briefly talk about for 1 or 2 lectures. But that's all.